module, I want to bring together all of the concepts and examples that we've looked at so far that have dealt with the geology of carbonate depositional associations, modern and ancient. I want to look at their commonalities across the platform. I want to compare the modern and the ancient. And for the first time, I want to look at the concept of evolution in terms of catastrophic change to the biotal community. We sometimes think of carbonate modelling across the Phanerozoic using the euphemism, the stage lights may flicker, yet the play goes on, even as the actors change. So look at this figure showing us that the distribution of the different components in carbonate sediments have evolved from the Archean through to today. The Precambrian was a time of profound abiogenic carbonate precipitation, calcium carbonate saturated oceans, and we had carbonate precipitation taking place in both benthic and pelagic realms. Much of that sediment was microbially bound. Some of it was microbially facilitated or even microbially driven in terms of the textures that we see in the microbial constructs, the stromatolites and the thrombolites. We pass from the Precambrian into the Cambrian through to the Jurassic. This is a time of skeletal invertebrate accumulations across the globe. It was also a time when we had abundant muddy mounds, especially in the Paleozoic, but passing up into the Mesozoic as well. We see these somewhat deeper water mud mounds, and we'll look at this in detail in this module, where we see abundant synsedimentary and microbial cements. Then as we pass from the mid-Mesozoic into the Cretaceous and the Holocene, we see a time dominated by pelagic carbonate sedimentation. The locus of carbonate sedimentation shifts from the platform into the open ocean. Within that framework, let's now focus in on the Phanerozoic and look at Metazoan evolution within carbonate skeletal framework buildups. So this diorama from the Natural History Museum in Chicago is showing us that life has evolved. In the Precambrian, we had algal stromatolites. That passed up into the Cambrian, where we see abundant archaeocyathids. The archaeocyathids go extinct by the Middle Cambrian, and we pass into zones where we see abundant, somewhat similar to modern associations of carbonate sediment contributors, the corals, the sponges, bryozoans, along with the calcareous sponges, the stromatoporoids. We then pass into the phyllid algal association, which is a deeper water mud mound association, then back into another time where we had combinations of corals, sponges, stromatoporoids until the end of the Cretaceous, rudists dominating the build-ups in the Cretaceous at the expense of the corals. Then we pass up into our modern associations of Scleractinian coralline algal associations that have dominated the reefal framework from the Neogene until the present day. But if we look at the general framework associations, if we look at the Silurian associations, we can see that we have a variety of stromatoporoids along with calcium microbes, which went extinct at the end of the Paleozoic, along with tabulate and rugose corals. One of the main predators at that time were the orthoconic nautiloid cephalopods, which as they jetted about the reefs were feeding on the trilobites, which went extinct in the Paleozoic, along with other prey. There were also at that time in that Silurian reef dense patches of pentamerid brachiopods living happily filtering food from the water column. Silurian reefal associations grew to 10 metres in the shallow waters of the platform interior, but attained heights of 100 metres on the shelf margin. At that time, these stromatoporoid coral reefal associations were the largest biological structures with the richest biodiversity up until that time that the world had seen. Now, within that framework of the evolution of the components of a carbonate platform, we see additional associations that were not dominated by the photozoans. We talk in quite a bit of detail about the contrast between the tropical factories, which are photozoan-dominated autotrophic organisms, along with animals such as corals, which had symbiotic relationships with photosynthetic algae, building these massive reef mounds. Within the modern, we see foraminifera polypod bivalve associations. At the same time, we see abiotic precipitates in the form of marine cements and ooids that vary with position and climate across the modern reefs of the world. Because it's a sheltered association, typically a framework association, mud-sized components can be quite common. Today we also have what's known as the temperate or the cool water factory, which is dominated by the heterotrophs, things that eat things. In that association, we can also have photoautotrophic organisms, the red algae and the symbiotic larger forams, extending to greater depths than we see the corals, and they can be quite significant components. But typically within that cool water carbonate association, we're seeing sediment dominated by sand to granule-sized skeletal hatches, and the phototropic shoalwater reefs and also the ooid shoals tend to be absent. Likewise, abundant carbonate mud and abiotic marine cements are not all that common in that heterozoan-dominated cool water factory. Then there's a third association, which is the muddy deeper water factory, which can build structures known as mud mounds, and we'll look at these in a bit of detail shortly. Those mud mounds, very common from the Cambrian through until the late Mesozoic, didn't seem to be able to raise the structure above the zone of permanent wave action. They didn't get above wave base. But they ranged across temperatures and depths which were much broader than today's tropical factories, and they had biotal communities were quite different than today, even though in the Carboniferous and the Permian, when these mud mounds were forming, we were looking at associations of Paleozoic icehouse climate. And we'll look at the climatic catastrophic emphasis a little later in this module. According to James and Jones, sedimentation rates on these ancient deep-water muddy mounds are comparable with those of a tropical faction. They exported less sediment than the tropical reefs and platforms, so overall their carbonate production was less than that of a tropical carbonate factory. That's the horizontal axis on this diagram, with 1 being the measure of the productivity of a modern photozoan factory. Across the board, the cool water carbonate factory and the muddy deep water carbonate factories were less productive than what we see in the highly efficient coralgal tropical associations of today. Mineralogically, we also see a contrast. Coming back to this diagram, marine precipitation can be both abiotic and biotic. It can be microbially induced or biotically induced, such as we see in most mud mound micrites. It can be a heterotrophic association, as we see in the cool water precipitates, or it can be the autotrophic association, as we see in the tropical water association. Mineralogically, there's a separation based on that factory metabolism, whereby the cool water precipitates tend to have higher contents of calcite and magnesium calcite. Mud mound associations can be magnesium calcite dominated, and then we have the tropical association, which can be aragonite dominated within this 3-part classification of ancient carbonate buildups. So that's the generalities across our carbonate depositional associations and the 3 major factories that we see. When we look back into the past, we need to think about how strictly can we apply uniformitarianism in terms of the modern tropical photozoan association. Remembering that life evolves, the stage lights may flicker, but the play goes on, although the main actors change. And that means that we don't really know, for example, what were the productive contributions of rudists or archaeocyathids. So it can be quite challenging to predict the outcomes in terms of sedimentation and volumes of sedimentation to interpret those features in the rock record. Clearly, when we look at the past, and this is a reconstruction of the Cambrian seafloor, which looks very different compared to the modern seafloor. This is for the Burgess Shale. Now, ancient reefs from the Cambrian through until the mid-tertiary are not simply analogues for modern reefs. They're made up of different organisms. In some cases, they had fundamentally different ecological structures and geological structures that don't have modern equivalents. I'm going to look at a few examples where we have variations in terms of the constituents and talk about the possibilities of variations in our carbonate models in terms of water depth, salinity tolerance, and so on. We'll look at the rudists, we'll look at the archaeocyathids, and we'll have a look at muddy, deeper water microbial associated mounds across the Paleozoic and up into the present day. Before we do that, let's go back and remind ourselves of 2 types of carbonate buildup and association that we see across the Phanerozoic. We see reefs versus reef mounds or mud mounds. So a reef is a massive or layered, laterally restricted carbonate construction that's forming in situ. It had relief on the seafloor, and it was built by the framework, the large meter-scale calcareous organisms. They might contain internal cavities. They also had sedimentary cement, both biological and abiological cements, cementing that reefal framework together. Compare that with the reef mounds, and these were once again laterally restricted carbonate bioconstructs, once again forming in situ. They had relief on the seafloor, but we don't see those megafauna, those skeletal frame builders. They contain much smaller skeletal components, sand, granule size, and they tend to be very rich in carbonate mud, along with internal cavities. In the Paleozoic, we see abundant stromatactus, along with marine sedimentary cements, creating a mud-dominated structure, which is in contrast to the framework-dominated structure that we see in a reef. If we put this concept of reefs and reef mounds now into a time framework, there is a range of ancient framework building organisms building the reefs, and those reef framework formers include the calcareous algae, the stromatoporoids, sponges, along with different types of corals, tabulate and rugose corals in the Paleozoic, with variable contributions of bryozoans and bivalves. Some of these framework builders were autotrophs. They were photosynthesizers. Other components in that reef were heterotrophic, but others were mixotrophic, where they had a symbiotic relationship with photosynthetic organisms living in their skeletons or in their cellular fluids, as we see today in that combination between the zooanthellae and modern-day corals. Across that broad range, from the Cambrian and through to the present day, most of the framework builders were clonal. They budded. They were also obligate calcifiers, sometimes dubbed hypercalcifiers for their ability to produce these large skeletons. Individuals can be as much as 3 meters or more in size in these hypercalcifiers. Modern-day corals are an example of our hypercalcifiers. Rudists were another example of hypercalcifiers. We also see bryozoans contributing all the way from early Paleozoic through until the modern. They also contributed not just in the photic, but because they are heterotrophic, we see them as major components in many deep water reefs and mounds, where once again these delicate fronds of the bryozoans served as a scaffold for automicrite formation and also for cement precipitation. We also see that the calcium microbes were significant contributors to the Paleozoic mud mounds and up through the Mesozoic mud mounds. But in both of those associations, we see inherently larger volumes of automicrite. These are the black lensoidal features in the diagram, where we see mud mounds, where we have automicrite, locally formed micrite, quite often microbially facilitated, accumulating in those mounds. We also see that the algae have played a role, both the green and the red algae, because they have calcified skeletons, and they can also break down to contribute mud into our various reefs and reef mounds. Some of the algae, as we see today in the modern reef, act as encrusters on actively growing framework. The calcium microbes back in the Paleozoic were acting as encrusters on our framework. In yet other times, we have what are predominantly skeletal microbial reef associations. This is the green lensoidal structures in the diagram, where we see what are biogenically dominated microbial reefs and mounds. And other times, there were combinations of both skeletal and microbial associations indicated by the blue, where the skeletal components were dominant, and these are known as the skeletal reefs. Also marked on this diagram, and we'll come back to this a little later, are the major extinction events on the right-hand side, shown by those black arrows. There are major changes in the makeup of reefs and carbonate platforms in general associated with the extinction events. What we see before the extinction event and after the extinction event can be quite distinctive in terms of the carbonate components in our reef. We see in the Paleozoic a rise in skeletal carbonates. We pass from the microbial association in the Precambrian with stromatolites and thrombolites into the early Paleozoic. The early Cambrian reefs were somewhat modern in structure, but they had a very different skeletal and vertebra association. So they were combinations of archaeocyathids, which went extinct in the Middle Cambrian, along with calcium microbes, which went extinct at the end of the Paleozoic, along with a range of sedimentary cements, internal cavities and borings. Archaeocyatid build-ups disappeared at the end of the early Cambrian. For a short time, the reef system regressed to a Precambrian style, with Middle and Upper Cambrian build-ups dominated by calcium microbes. By the time we reach the lower Ordovician, we see the evolution of the corals, the bryozoans, and the stromatoporoids that are locally encrusting small skeletal microbial mounds. By the middle to the late Ordovician into the Silurian, we're seeing this great biodiversification. We're seeing the acme of the Paleozoic reefs, Most of the reefs at that time were framework associations that were skeletal reefs, or combinations of skeletal calciumicrobial mounds, with the main reef form as a consortium of stromatoporoids, corals, and calcium microbes. That was a period in the Devonian of seemingly unrestrained reef growth, but it was brought to an end in the late Devonian via the progressive extinction of various stromatoporoid groups. By the time we get to the latest Devonian, stromatoporoids are no longer major contributors to the reef, but we see the reef mounds dominated once again by calcium microbes. With the extinction of those invertebrates within that reef framework, the reefs during the late Paleozoic were mostly reef mounds, skeletal mounds, or calciumicrobial skeletal associations. Evolution of reef components have occurred as long ago as the Paleozoic. Certainly by the time we get to the shallow water Mississippian reefs, we're seeing a range of endemic communities making laminated microbial mounds, mud mounds, with a rich encrusting open surface along with a cryptic fauna living in cavities, associations of algae, bryozoans, some corals and sponges. By late Paleozoic times, we're getting into a development of spectacular outer ramp mud mounds. These are the Walsaudian mud mounds we'll look at shortly. They could be up to 150 metres above the surrounds. Most of those mud mounds were what we called polymuds, where they're combinations of different mud origins, allomicrite and automicrite, along with prolific marine cements. By the middle to late Permian, a different association as we shift toward aragonitic producers. We pass from tabulate and rugose coral associations of the Ordovician into the specialized calcareous sponges along with phyllid algae as the primary builders until the end Permian extinction, taking out the Paleozoic reef clay. In the Mesozoic, we see the recovery period as reefs are no longer present in the Triassic until we start to see a transition into corals, which were scleractinian corals. These are the modern reef builders. Tabulate and rugose corals, which contributed significant volumes to the Devonian reefs, had gone extinct by the end of the Permian. Scleractinian corals, along with calcifying sponges, appear in the Triassic. As we go from the Jurassic into the Cretaceous, we start to see a transition where we have rudists, a bivalve, these large cone-shaped mollusks becoming dominant in many of the tropical regions, with a climax community outcompeting the corals for the photozoan reef space. At the same time, we see what's known as the mid-Mesozoic revolution, where we see the explosive success of the calcareous plankton, especially the coccolithophores. We start to form chalks. For the first time in Earth history, significant carbonate deposition has moved from the shallow shelves into the deep seafloor. This creates a global chemical buffer that ameliorates fluctuations in Earth climate over geological timeframes. The end Cretaceous extinction wiped out the rudists and it modernized the reef ecosystem. From the Paleogene to the Neogene, we see coralline red algae and larger benthic foram becoming major contributors to the carbonate platforms. From there, as we go into the Neogene, into the modern era, we see scleractinian corals regaining their dominant position as they had in the Triassic. They were the main primary framework builders, and they're supported by their symbiotic algae, their zooanthellae. This allows for extremely high calcification rates, the hypercalcifying rates, in what were oligotrophic or nutrient-poor waters. Let's now put that into the framework of extinction events. I'll give you a quote from Gould, who said, "Life is a copiously branching bush that's continuously pruned by the grim reaper of extinction. It's not a ladder of predictable process." The way in which we consider evolution has changed drastically in the last half century, from Darwinian gradual evolution into global catastrophic events, greatly decimating the world's population. If we put that into a time-based framework where we look at the different contributors to the reefs across time, from the Cambrian through to the Neogene, there is a cycle. The first one ends at the end of the Devonian with the major extinction of corals, but there's an earlier extinction event where corals and coralline sponges go extinct. The calcium microbes are lessened at the end of the Ordovician. Then the next cycle after the Devonian extinction comes into its own. We start to see algae becoming dominant components. Then we see once again reefs and reef mounds coming to an acme at the end of the Jurassic. Then there's the Triassic extinction event. Another cycle comes through. We start to see corals coming to dominate again by the end Triassic event. Then across the Cretaceous, we see rudists, the orange, the pelecypods, the bivalves, as the major reef formers, mound formers. And then from the Paleogene onwards, we see another coral coralline algal cycle building until we reach the present day. So, as Kissling showed in those papers back in 1999 and 2010, reefs do well when we have framework corals and/or coralline sponges in the ascendancy. But those cycles are susceptible to extinction events. So extinction is playing a role throughout the Phanerozoic in the major components that are contributing to our carbonate buildup. Just a short 101 paleontology here. We'll just look at definitions of extinction. These days we think of extinction events, this was summarized by Raup in his groundbreaking book back in 1991, where we can break mass extinction intervals relative to background extinction into three types, what we call the fair game, the field of bullets, and wanton destruction. The fair game extinction scenario is the Darwinian view of extinction, where organisms with traits consistently related to environmental fitness face greater risk of success or extinction during background time. And that selectivity pattern persists during mass extinctions, so this is an ongoing throughout the Phanerozoic. But of course, during mass extinctions, more taxa are lost overall. For example, if we look at trilobites, they underwent a gradual demise across the Paleozoic. Then we have the field of bullets extinction scenario, where mass extinction is non-selective and taxa are lost randomly regardless of the traits that are affecting their fitness during the background times, the fair game times. So, for example, we can think of the end Cretaceous that nearly wiped out most planktonic foraminifera. Lastly, we have the wanton destruction scenario, also known as the non-constructive selection scenario, which describes this shift from background extinction. In this case, survivorship during the mass extinction is not determined by fitness-related traits that are relevant during background times, fair game times. Rather, selection is tied to the chance possession of traits that enhance survival during this catastrophic mass extinction event. This is regardless of their usual significance. So, for example, in terms of us, we can think of the end Cretaceous survival of small nocturnal mammals over the massive dinosaurs. The dinosaurs were wiped out. Things living in burrows, the mammals, tended to be small. They had the ability to eat detritus and buried roots and organics. They became the only traits that mattered in a nuclear winter when the primary food chain had collapsed. Extinction overrides fair game evolution. Wanton destruction, or the field of bullets notions, override the fair game modes of evolution at particular times in the past. Those blots on the timeline, or the arrows on the earlier evolutionary association, show us the significance of those extinction events in terms of extinction rates. And I put two curves up there, one by Foote in 2007, one by Koski in 2017, showing us the importance of extinction events. Coming back to the curves of carbonate contribution, you can see that those extinction events are controlling the major components in our platform. What I want to do in the next section is look at how ancient carbonate associations were similar but different because of mass extinctions, changing the nature of carbonate buildups across the Phanerozoic.